Here is the truth function for the conditional. If P then Q. It's true when the antecedent and the consequent are true. It's false when the antecedent is true but the consequent is false. And then it's true when the antecedent is false, whatever the truth value of the consequent. So like the disjunction, the conditional is true on 3 of the 4 lines, and that means you don't know very much. You don't know very much when you know a conditional is true. What extra piece of information would allow you to prove the consequent of the conditional, Q? Well, trivially, you could discover Q is true. Someone could tell you Q is true, but then the conditional would play no role. But suppose you found out, you know that if P then Q is true, so you know on line 1, or line 3, or line 4. Well, if you discovered the antecedent was false, that would tell you you're on either 3 or 4, because those are the 2 lines on which P is false. That wouldn't tell you anything, because you might be on line 3 where Q is true, or you might be on line 4 where Q is false. But if you discover that P is true, then you immediately know that Q is true, because P is true on the top 2 lines. If P then Q is true only on the top line and the 3rd and 4th, but so if you know P is true, you know you're on line 1 or line 2. If you know if P then Q is true, you know you're on line 1 or 3 or 4. So if you know both things are true, you know you must be on line 1 where Q is true. And so the rule that is called in the book arrow elimination, whenever you have a conditional and you also have its consequent, then you can prove. So if you also have, let me start all of that again. Whenever you have a conditional and you have its antecedent, then you can prove its consequent. That is a valid sequence. But if you know if P then Q and Q, you don't know whether P is true. That's actually a fallacy, the fallacy of affirming the consequent. If Chi is in Paris, then Chi is in France. Chi is in France, so Chi is in Paris. That is not valid. This corresponds to if Chi is in Paris and Chi is in France, Chi is in Paris, therefore Chi is in France. And obviously that is truth preserved. So we might have a sequent how could we prove it? Well, our first assumption is the atomic center is P. And our next assumption is a conditional. It's a conditional that has a disjunction as its antecedent, right? And what we're trying to prove is a conjunction, both P and R, right? And our job in doing the proof is to fill in the gap with truth-preserving steps. Well, if you look at your conclusion here, which we're trying to prove just on assumptions 1 and 2, it's a conjunction. Its left conjunct is P, and we already have that on line 1. So we know we can get the left conjunct of our conclusion. We'll use ampersand introduction, right? And that will give us, so we've got the left, and all we need then is the right conjunct, R. So, when we begin, we think, okay, we have to prove both P and R. Then we look at our premises and we see we already have P. So, really, the job is just to prove R, and then we can put it together with P by ampersand introduction to make both P and R. But we don't have R up here. We have P, and we have if either P or Q, then R. Well, arrow elimination allows us to prove the consequence of a conditional if we have the antecedent. So what we need is either P or Q, right? That's the antecedent of the conditional. R is the consequence of the conditional, either P or Q is the antecedent. And we can use wedge introduction to get this. So one, wedge introduction. If the sentence on line 1 is true, then the sentence on line 3 must be true. Because this says P is true, and this says either P or Q is true. Where does Q come from? It comes out of logical space. And now we have on line 3 the antecedent of the conditional on line 2. So we can here write 2, 3, arrow elimination. Here is a conditional, here is its antecedent. What I prove is its consequent, right? This is the same sentence as this is the same sentence as the antecedent. And so now we've proved the conjunction, both P and R, from our two premises, P and if either P or Q, then R. Wedge introduction gives us either P or Q. Arrow elimination from 2 and 3 together, so arrow elimination is a 2-line rule. And then the 2-line rule ampersand introduction, and we prove our conclusion. So arrow elimination is the rule that allows us, when we have a conditional and we have its antecedent, then we can prove its consequent. There's no rule for proving the antecedent of a condition. Thou shalt not prove the antecedent, because the truth of the antecedent never follows from the truth of the conditional, not even if you know the consequent of the conditional is true. So that's why, and remember, this is related to the fact that the conditional is asymmetric, that whereas you can flip the conjuncts of a conjunction or the disjuncts of a disjunction or the sentences either side of a biconditional, you can flip them around and the truth value stays the same. But with the conditional that is not true. And so there's, so to speak, only one version of arrow elimination. Conditional plus its antecedent allows you to derive its consequent. This rule is very often called modus ponens, or modus ponendo ponens. And there is another rule related to the conditional which has a similar name, modus tollens. But that is not a primitive rule in our system. Here's what it looks like. When you have a conditional and you have the denial of the consequent, you can prove the denial of the antecedent. If P then Q, but not Q, so not P. If Chi is in Paris, then Chi is in France, but Chi is not in France, so Chi is not in Paris. But in the system that we are using, modus tollens is not a primitive rule of proof. It's a so-called derived rule of proof that we have to prove using the primitive rules, and then we can use modus tollens. So As far as the primitive rules are concerned, we just have arrow elimination or modus ponens. When you have a conditional and you have its antecedent, then you can prove its consequence.